want to do today then is just begin with another example problem. In fact, I'll end with an example problem as well. Basically, that's the same thing as this. This is just my copy in my notebook. So I'll move this now. So we'll do two example problems today. And hopefully, after you see these two examples, you have a much better feel for the nature of the kind of problems that you're going to be dealing with in this class. By the way, the midterm exam is going to cover through section 4.2, which is problem solving for first law for closed systems. And again, it's through today's material, through the homework that's due next week. All right, so we've looked at a couple example problems already. Both of those were sealed rigid vessel types of problems. And now we're going to look at something a little bit different. I actually put this on the board last time, but today we're going to actually solve through this problem. This does say problem 132, but it's actually from the 6th edition. We're up to the 8th edition now, so you're not going to find this in your textbook. So I've put it up here, and I'll just leave it up there for a little while longer as I'm starting to set up this problem. So as usual, let's read through it. So we have a mass, 0.2 kilograms of saturated R134A. And it's contained in a piston cylinder device, which is at 200 kilopascal. It says initially 75% of the mass is in the liquid phase, which of course means 25% vapor. It says now heat is transferred to the refrigerant at constant pressure until the cylinder contains vapor only. All right. Now I will note that the author could have just simply said that this was a frictionless vertical piston cylinder device, which automatically means that it's a constant pressure process. Instead, the author gave you the initial pressure and then said that heat transfer occurs at constant pressure. So either way, it's a constant pressure process. Anyway, show this process on the PV diagram, determine the volume occupied by the refrigerant at the initial state, the work done, and the total heat transfer. All right, so that is this problem. So for 132, edition 6. Okay. 4. All right, so the first thing I always like to do is draw a sketch and make sure that I show all the information that's known and unknown. So this one is a piston cylinder device. So basically, I would show a piston cylinder. We're given the mass. So 0.2 kilograms. It's R134A. So I note the substance. It says it's saturated, and then it tells me the percentage mass in the liquid phase. Oh, I'm sorry. First it tells me the initial pressure. So I'll just put P1 is equal to 200 kilopascal. All right, now it tells me that initially 75% of the mass is in the liquid phase, and we all know that the author did this to us on the last problem, right? We need the quality, which is a percentage vapor phase, not the percentage liquid phase. So 75% liquid obviously means 25% vapor. So the quality is given as 0.25. It says heat is transferred. It doesn't tell us which way heat is transferred, just that heat is transferred. So I'll show Q with kind of ambiguous arrows. And then it says transferred at constant pressure until the cylinder contains vapor only. All right. So constant pressure, so I'll just say that P1 is also equal to P2. And now it starts as a two-phase mixture. At the point where it contains vapor only is where we hit the saturated vapor line, right? So we definitely know that we're a saturated vapor at 0.2. So 2 is a saturated vapor. And we want to show this on a PV diagram. And we want to find the volume occupied initially. And we want to find the work. And we want to find the heat transfer. All right, so this pretty much sets up the problem. Now, let's just start this one by showing it on the PV diagram. Even though I don't necessarily have to do this immediately, it does make a certain amount of sense to do so. We note that we start as a reasonably high quality two-phase mixture, And since we're moving at constant pressure, and this is a PV diagram, then that means we have to be moving to the right, right? Moving along the constant pressure line. And at the point where it finally becomes all vapor, that's right there on the saturated vapor line. So there's my state point 2. If this problem said that heat was added until it becomes superheated, well, I mean, we could perhaps show an entire constant pressure line as they look like that, and then we would show point 2 being somewhere up here above saturated vapor line, but not for this problem, right? I'm sorry, I didn't do this right. This is the PV diagram. I'm thinking TV diagram. Constant temperature lines kind of work like that. Nonetheless, it doesn't matter. If it's superheated vapor, then clearly we've added heat beyond the point where it's a saturated vapor, and that's not what we want, right? This problem ends when the cylinder contains only vapor, and there you have it. Yes?
0.25 is considered a high quality as far as the volume ratio is concerned? And so far to the right?
You know what? I didn't really say that properly. Yeah, 75% would be high quality, but that's the percentage of liquid. 25% is a relatively low quality. Honestly, it's still probably going to be near the right-hand side because after all, even though the vapor is only 25% by mass, its specific volume at this pretty low pressure is going to be about 1,000 times greater than the specific volume of the liquid. So even though it's only 25% by mass, it might be more like 80 or 90% by volume, and this is a volume axis here. So it is very possible that point 1 is far to the right like this. I don't really know for sure until I go through the numbers, but you know, at least this is accurate. You know, horizontal from 1 to 2. All right, so what next do we need to do? Well, let's make sure we know what to assume, what not to assume. First of all, there's no kinetic energy change, as is the case with essentially all these problems, right? There's no velocity associated with the substance that's in that cylinder. What about the potential energy? Clearly there's going to be a height change, right? I mean, the volume is increasing, so the piston does have to move upwards. However, what you find is that potential energy changes have to be, well, I'm sorry, let me rephrase that. Height changes have to be very significant before there's any meaningful and measurable change in potential energy. Usually you would have to have a height change of, you know, something on the order of several meters before that potential energy is not negligible. So here we're talking about a really small mass of material. I don't know what the total volume is, but it's not that great. And you know, even if the cylinder rose significantly, there's still not going to be several meters of height change. So it makes sense to assume that there's no change in the potential energy. Okay, so that's typical of these kind of problems. I might also note, I have no way to quantify that even if I wanted to. I don't know if this is a short, squat cylinder, which is going to increase a fraction, or if it's a tall, skinny cylinder that's going to increase significantly. They don't tell me anything about the geometry of that cylinder, so even if I wanted to find the height change, I have no way to do so. So I just have to assume that there's no change in potential energy. Okay. Now, there definitely will be some heat transfer. There'll definitely be some work. We know that work in this problem is all boundary work, right? There's no electric resistance work. There's nothing like that. And for a constant pressure process, this is mass times pressure times change in specific volume. Remember, this is boundary work, but for constant pressure only. All right? So that's how we're going to find the work. And then we're always going to need the first law. The heat transfer is the change in internal energy plus changes in kinetic and potential energy plus the work. By the way, if I was able to quantify the kinetic and potential energy, I would definitely write out the equations. But here, we know there's 0, so I mean, why bother? We'll just show delta KE and delta PE and just show them equal to 0. So this is the basic equation that we need to solve for. So now the question is, can we find everything that we're looking for? Not quite yet. What about the volume at point 1? The only way to find the volume is to know the mass and the specific volume. And fortunately, I can find that, right? So I'll also note If I define the initial volume, it's just mass times specific volume, that is initial specific volume. I'm given the mass, and I need V1. So with these equations, we'll ask ourselves, do we have enough information now to solve the problem? So before I even solve anything, we just say, well, yeah, right? We know that as long as we know my two state points 1 and 2, I can go into my property tables and I can find any property I want. Now, quality counts as a property, right? So we know the pressure and that the quality is 25%. So yes, we know state point 1. We can find V1 as just VF plus quality times VFG. We can find U1, just the quality times UF, just UF plus the quality times UFG. So we know state point 1. State point 2 is given. Pressure at 2 is given. It's the same as 1. What about state 2? Well, again, we need two properties, and we have them. We know that the pressure is still 200, but we also know that it's a saturated vapor, meaning that the quality is 100%. We know that at state point 2, V is just VG, U is just UG, right? Saturated vapors. So we have both thermodynamic states. We can find everything shown down here on the page. So now it's just a matter of going through a little bit of mathematics. I will note that because we're talking about R134A and we're in the SI system, then we're going to have to use tables A11 and A12. A13 is the superheat table, but we don't have superheated vapor anywhere in the problem, so we'll just use A11 and A12. And in fact, we really don't have the temperature anywhere in the problem either. We're given pressure at points 1 and 2. So really, it's just A12 that we're going to use our saturation pressure table. So all the data is going to come out of there. Now we can work on this problem. So let's just find our thermodynamic property data first. And we'll start at state point 1. So at P1 and at the quality at 1, we go into table A12. Now let me get rid of the problem statement and put the property tables up. Okay, so A12. All right, so here's table A12, the saturated R134A pressure table. And all the data we need is going to be at 200, right? So we go to the right table, we know the pressure, we read across, we need both VF and VFG. Of course, we don't have VFG, it's not printed in the book. I don't know why the author just didn't add one more column and give you the VFG data, but he didn't. So V1 is VF plus the quality times VFG, but we know VFG is just VG minus VF. All right, so this is the equation we have to solve for. So let's just pull the numbers out of our table. You can see them right over here. So we go down to the 200 PSIA line, kilopascal line. We read across, and VF is 0.007532. The quality is 25%. By the way, I should put X1 over here just to make sure we know this is the initial quality. Anyway, quality is 0.25, and then VG is 0.099951 minus VF, so 0.0007532. And if we just go through the mathematics, we end up with V1 of 0.02555 cubic meters per kilogram. So there's V1. And we do U1 exactly the same way. This is UF plus the quality times UFG, and there is UFG data in this book. So again, just go to the 200 kilopascal line, read across to the 5th and 6th columns. UF is shown as 38.26, and then plus the quality times UFG, which is 186.25. Oh, yeah. And then, again, the units are all kilojoules per kilogram. We go through a little math, and we get 84.82 kilojoules per kilogram. By the way, one thing I want to note, sometimes I may have some incorrect numbers in some of my problems that I'm solving in class, or even some of the problems I posted on the blackboard or on the board outside my office. You know, conventions are held like, I don't know, every 5 years or so by the international community, and new research is presented, and the tables change. You know, new data becomes available for refrigerants or water or whatever. So periodically, the various governing bodies, usually it's ASME, will then print new property data. So if you look at the property tables from the 6th edition of this textbook, which is I think about 7 or 8 years old now, compared to the property tables that are in the 8th edition, the numbers will be slightly different. Not all of them. The refrigerant tables didn't change, the water tables changed, or maybe it was the other way around. It doesn't matter. I fixed everything on this problem, and I've tried real hard to fix everything on all the problems that I've used in the past, but I might miss something a little bit. I have noticed that some of you are indeed using old thermodynamic property tables, presumably from some old book that you have. I know that because some of your numbers are subtly different, you know, maybe just off down in the 3rd or 4th decimal place, but some of you are using numbers that aren't correct. So that's okay, I'll still accept that, but I just want you to be aware that the numbers do change periodically. All right, so back to the problem. Let's also find the volume at this point. So that's the mass times the specific volume. So 0.2 kilograms times 0.2555 cubic meters per kilogram. And that's going to give me 0.00511 cubic meters. So kilograms cancel. And there's the first thing that we're looking for, the volume. All right, next, let's find the thermodynamic property data at state point 2. So at P2, saturated vapor, we're still in table A12. So V1 is equal to VG. And again, we just go to the table. In fact, VG is already here. It's the same 0.09995 that was up at the top. So 0.0999. Oh, yeah. I'm so sorry. It is 0.2. I mean, I put P2 saturated vapor, but then I wrote and said V1. This is 0.2, the saturated vapor. So V2 is VG, so it's 0.099951 cubic meters per kilogram. And similarly, U2 is UG, which is then going to be 224.51 kilojoules per kilogram. So we have all the data that we need for the problem. Just 2 things left, right? We can find the work, we plug it into the first law, we find the heat, we're done. So work first. So the work, and I'll just rewrite the equation. So we have 0.2 kilograms. Our pressure is 200 kilopascals. Then 0.099951 minus 0.02555 meters cubed per kilogram. You know, as usual, you look at those units, and the units clearly don't look correct. I mean, where's the kilojoules in all this? But as usual, let's just remember that a kilopascal is the same thing as a kilonewton per square meter, and a kilojoule is the same thing as a kilonewton meter. So we can just cancel out all the units here, and everything cancels. Mass cancels, cubic meters cancels, kilopascals cancels, kilonewtons cancels. We just are left with kilojoules, right? So as long as you're in the SI system solving for work, there's no unit issues. Everything's an identity with regard to these conversion factors, so it works out easily. Caution, in the British system, it's not going to work out this easily. It will definitely not work out this easily. You know, you'll have PSIA for your pressure units, and then cubic feet per pound. A PSIA cubic foot is not the same thing as a BTU. You're going to have to go into the conversion factors, which is in the inside back cover of your book, or in my case, the last page of the handout. And you'll find the conversion factor you need. In fact, it's right here where the cursor is. Why the cursor turned to an X, I don't know, but it's right here. It says 1 BTU equals 5.40395 PSIA foot cubed. So all the conversions you need are in the book somewhere, but follow through with the units. If you don't follow through with the units, there will be some errors. All right, so no unit issues. We go through the mathematics and we find that the work is 2.98 kilojoules. And it's a positive number, which it's supposed to be, right? The volume is increasing. The piston is moving upwards. Work is being done by the system as it pushes into the piston and moves it upwards. So work done by the system is positive, and that's a positive number. So that gives us some confidence. Lastly, heat transfer. All right, so heat transfer is found with the first law. Again, I'll rewrite the equation. So it's really just a matter of plugging in all the numbers we already have. So 0.2 kilograms, U2 minus U1, so 224.51 minus 84.82. Those are both kilojoules per kilogram, plus 2.98 kilojoules. The units work out just fine. We go through the mathematics, and we end up with 30.9 kilojoules. So that is this problem. Any questions? There is an alternate way to find the heat transfer, isn't there? Remember that if we have a constant pressure problem, we can use enthalpy instead of internal energy, as long as we do it properly. I would note that for a constant pressure process, we still have the same equation, right? I mean, this is our basic equation. However, the boundary work is mass times pressure times change in specific volume. We remember that U2 and P2V2 is H2, and U1 plus P1V1 is H1. So it turns out that if we wanted to, we could just as easily have found the total heat transfer for a constant pressure process only, and this is a constant pressure process, right? But we could have found it just as easily by finding H2 and H1. I could have gone back to state point 1 and I say H1 equals HF plus quality times HFG. H2 is just HG, right? And I could have found the heat transfer in a slightly more direct fashion. Now you may wonder, well, why didn't I do it if it's a little bit easier to do it that way? Well, the reason I didn't do it is because the author asked me to calculate the work. If I have to calculate the work anyway, what does it really matter? I mean, I'm going to need to find most of this thermodynamic property data. It doesn't really save me any time. As long as I have to find the work, I might as well just use the internal energy. But you can do it both ways. In fact, I would suggest do it both ways. For constant pressure problems, if you don't get the same answer, you've done something wrong. So it's a good learning tool. Anyway, questions? Good. So this brings us to a difficult problem. As if this last one wasn't hard enough, right? These are not really that complicated once you've tried them. There's a lot of them, and they're all a little bit different. But this next one is a little more complicated than most. So it's this problem here. Well, there we go. So this is out of the current edition of this textbook, and this is problem 4-139. So let me read it. You have a piston cylinder device which initially contains 0.35 kilograms of steam at 3.5 megapascals superheated by 7.4 degrees Celsius. By the way, that's not the temperature. That's the number of degrees above the saturation temperature. When it tells you superheated by a certain number of degrees, that's the temperature above the saturation. So we know we can go into the steam tables at any pressure and find the corresponding saturation temperature. The temperature initially is 7.4 degrees higher than that. So make sure you're aware of that. It says now the steam loses heat to the surroundings and the piston moves down, hitting a set of stops, at which point the cylinder contains saturated liquid water. So the first part of the problem, and what makes this hard is it's a two-part problem. The first part of the problem, honestly, is not a whole lot different than the last problem. You know, you start with a piston, unlike the last problem where you add heat and the piston moves up. So far, this problem starts with something superheated and you remove heat and the piston moves down. So it's the same problem as the last problem, but only up to that intermediate point. And this is where things get difficult. It says the cooling now continues until the cylinder contains water at 200 degrees Celsius. By the way, when the author uses the word water, he doesn't mean saturated water, doesn't mean liquid water, it doesn't mean vapor water. It could be anything. It could be any phase. So all we know is that it's at 200 degrees at that final point. So the cooling will continue. We finally get to 200 degrees Celsius, and that's when the problem ends. Now, isn't the second part of the problem really the same problem as the one we did at the end last time? It's just a constant volume problem, isn't it? Once that piston comes down and hits the stops, it can't move anymore. The volume is constant inside that cylinder. The mass is clearly constant. So this is a constant volume process. So this particular problem is a two-part problem. You do the first part, let's call it from 1 to 2, which is a constant pressure process. And then you do the second part, which is from 2 to 3, let's just call that last point 3, which is a constant volume problem. All right, so 4-139. And we know that from 1 to 2 is constant pressure, and from 2 to 3 is constant volume. Okay. So in other words, P1 equals P2, V2 equals V3. I've seen problems like this that are reversed, where it starts sitting on the stops as a constant volume problem, and then when enough heat is added, then the liquid starts to vaporize and the piston starts moving upwards. So, you know, I could certainly look at these problems in both directions. All right, so we now have some information about the problem. First of all, any questions just conceptually? Everybody should understand how this is just a constant pressure problem followed immediately by a constant volume problem, that the end of the constant pressure problem is the beginning of the constant volume problem, right? All right. So now let us create the right sketches. All right, so here's my piston cylinder device, and then at some point down here are the stops. This represents state point 1. As the piston moves down and sits on top of the stops here, I'll just show this as a dashed line, then that's going to represent state point 2, and it's also going to represent state point 3, right? So this is just the illustration. So now let's write down what we know and what we don't know. Oh, by the way, there's one thing I should point out about this problem that I forgot to mention. I'm not really happy with the way the author worded the problem. He really should have used the word frictionless vertical piston cylinder device. Now, granted, there's a diagram in the book, so it should be very obvious, but it may not be obvious to you as you're first learning this material. The fact that it's a frictionless vertical piston cylinder device means that it's a constant pressure process, right? We know that. We've seen problems like this before, but they don't tell me that. The previous problem said that the piston moves under constant pressure, so it was obvious. In this problem, the author has not done well. So if I give you a problem like this, or any piston cylinder problem on the exam, I'll make sure you know whether it's a vertical frictionless piston cylinder device or just some random piston cylinder device that is, say, moving horizontally at some odd angle, such that the pressure is not constant. So I'll make sure it's clear to you. In this problem, anyway, it's a constant pressure process from 1 to 2. All right, back to the problem. So we know the mass as 0.35 kilograms. We know that it's steam, In other words, H2O. By the way, when I write my own problems, I just use H2O. I don't even use the word water because I don't want to confuse anybody. So I'll just say H2O and then let you figure out what the phase is. All right, so it's H2O. It's superheated by 7.4 degrees. Therefore, T1 is equal to Tsat plus 7.4 degrees. And we'll figure out what that value is shortly. But at least we know that T1 is not the saturation temperature. It's a certain number of degrees above the saturation temperature. Okay, steam loses heat to the surroundings. So there's heat transfer out of the system. And the piston moves down. So there is some heat transfer from 1 to 2. Eventually it hits the stops, at which point the cylinder contains saturated liquid water. So 2 is sat liquid. All right. Again, we know now that as the cooling continues, the temperature is going to drop some more. The volume is going to remain constant. But finally we get to point 3, and it tells me that T3 is 200 degrees Celsius. All right. And let's see. Oh yeah, I forgot to write down the steam pressure at point 1. So up here at 1, I should have said that P1 is equal to 3.5 megapascals. That was given in the problem statement. All right. Okay, so what are we trying to find? We're trying to find the final pressure and the final quality if it's a mixture. And let's keep in mind that the final is 0.3, not 0.2, right? And then we also would note that we're trying to find the quality if indeed it's a two-phase mixture. It also asks us to find the boundary work. It also asks us to find the amount of heat transfer when the piston first hits the stops. So that's really Q12. But it also asks me to find the total heat transfer. So that's the sum of the heat transfer from 1 to 2 and 2 to 3. So Q total is Q1 to 3, which, by the way, is equal to the sum of the heat transfer for the first part from 1 to 2, and then plus the heat transfer from 2 to 3. Okay, so this is something that we're trying to find for this particular problem. So before we actually go through, let me show this also on a appropriate diagram. How if we use a TV diagram? I'll just put this over here on the side. There's my saturation line. And there's a constant pressure line. All right, so we know that we start as a superheated vapor. It's not that superheated. I mean, only 7 degrees above saturation, so it's going to be pretty close to the saturated vapor line. It says that point 2 is when it hits the stops, and it's all saturated liquid. So it's a constant pressure process, so we're going to follow the constant pressure line down to the saturated vapor line, all the way over until we finally get to the saturated liquid line, so there's state point 2. And then we have a constant volume process, right? Now, note it's a closed system. The volume's constant, the mass is constant, the specific volume is therefore constant. And because we're cooling, the temperature is going to drop, and we'll end up with state point 3. That's right there, directly below state point 2. So here's our initial setup. Not really quite done with the setup, mostly done with the setup. What about some assumptions to make and some equations and all that? Well, like the previous problem, we'll note that there's no velocity associated with the water that's inside this container, so there's no kinetic energy change. We'll also note that the height change is probably minimal, but we don't know for sure just because we don't have any geometry data, so we'll just have to assume that this is a pretty small system. I mean, it's just 1/3 of a kilogram. That's not much, so we can note that we'll assume that there's no change in potential energy. All right? What about the work? That's something we should talk about. Well, the work from 1 to 2 is constant pressure work, right? So that's just going to be the mass well, I'm sorry, let me first say it's just boundary work, right? There's no electric resistance, there's no other forms of work. So the work from 1 to 2 is all boundary work. And this for a constant pressure process is mass times pressure times change in specific volume. Okay. Again, constant P only. So that's the work we have from 1 to 2. What about the work from 2 to 3? Yeah, it's 0, right? It's a constant volume process. Again, I should first write that this is the boundary work, no other forms of work, and then that's just the integral of P dV from 2 to 3, but there is no change in volume, so it's 0. I mean, we talked about this before. You don't have to write all this out. If you recognize that constant volume problems have no work, then just say work is equal to 0. So this gives us our work terms. And then what about the heat transfer? Well, the heat transfer, first we'll look at 1 to 2, and then we'll move on to the next part. So the heat transfer is the change in internal energy plus the change in kinetic and potential energies, and then plus the work. We know there's no kinetic or potential energy changes. So the heat transfer from 1 to 2 is just this, and of course the work we found earlier using this equation. So this is going to be how we're going to find the heat transfer. By the way, since the author specifically asked me to find the amount of work, I don't have to use the enthalpy version of the first law that applies to these closed systems for constant pressure processes, right? I could write Q equals simply mass times H2 minus H1, but again, there's no need. I already have the work, so I'm just going to leave it in this form. All right. So there's the heat transfer from 1 to 2. Now, to write the heat transfer from 2 to 3, maybe I'll just do it this way. We'll note that the heat transfer from 1 to 3 is just the sum of the heat transfer from 1 to 2 plus the heat transfer from 2 to 3, right? We know the heat transfer from 1 to 2 is above. So M U2 minus U1, then plus MP V2 minus V1. So there's the heat transfer from 1 to 2. What about the heat transfer from 2 to 3? Well, again, there's no kinetic energy change. There's no potential energy change. There's no work. So the only heat transfer we have from 2 to 3 is just a change in the internal energy, right? So this is just M U3 minus U2. Okay. Maybe what I should do to make it more clear is note that this is equal to the following. And all three of these terms are now 0. So we get this. And then we'll note that the M2 U2s cancel, and we simply get M U3 minus U1, and then plus the boundary work from 1 to 2. And this is how we're going to find the heat transfer. Thank you. So the equations are the same equations. If this isn't clear, then you just need to study more. There's not a whole lot of difference between this problem, the last problem, the two we did last time. They're first law problems for closed systems. They use the same general version of all the equations. They're slightly different. The work's sometimes slightly different. The heat transfer might be found slightly different, but they're all the same. All these problems here in Chapter 4 are the same problem, but with variations. Yes?
So when it says that it hits the stops when it's saturated vapor, that's telling us that V2 is going to be VF, right?
Yes, liquid, yeah. Okay. All right, so what do we want to do next? Not much more to do, right, except get our property data. Do we have two independent intensive properties at each of the three state points? And if the answer is yes, then we're done. So let's think about it. We know the pressure and we know the temperature at point 1, although I haven't calculated the temperature yet, but I know them both. So yep, state point 1 is known, superheated, pressure and temperature independent, intensive. We have state point 1, meaning we can find V1, we can find U1. Okay, what about state point 2? Yes, right, we know that the pressure at 1 and 2 are the same. We have the pressure and we know it's a saturated liquid. So state point 2 is known. We have VF, we have UF if we need it, although we don't need it. And then what about at point 3? Well, we know that it's a constant volume process. So we know the specific volume at state point 2. That has to equal the specific volume at state point 3. So we know that information. And we're also told that the temperature at point 3 is 200 degrees Celsius. So again, we have two properties. We have volume and temperature, specific volume and temperature, I should say. Again, independent intensive properties, so state point 3 is known. So as long as we recognize that we're using the first law in its variations and we're using the data that we all have, the rest of this problem is really just a matter of pulling data out of tables and chugging away. So we'll do that next. Let me pull the steam tables up. By the way, SI units, we've got superheat, we've got two-phase mixture. We're going to use A4, 5, and 6 as we solve this problem. So that's worth noting here as well. All right, so hopefully you have all this written down. It didn't work. I've never owned a PC in my life. I'm a Mac person. Although I do have one of those Surface Pro computers, which is kind of I won't say anything. They work nice, but my iPad's better. Okay, so I had to say something. Yeah, I don't know. I guess PCs are just cheaper, aren't they? Okay, so that's not what I want. There we go. All right, so 4, 5, and 6. So let's just start at A5. So here's A5. We really would like to know what the temperature is at state point 1. So let's just start there. So the temperature at 1 is the saturation temperature at the pressure of 1 plus 7.4. So the saturation temperature at, was it 200? No, 3.5 megapascals, quite a bit higher. So on to the next page. There we go. 3,500. So that's 242.56 plus 7.4. And why don't we just call it 250 degrees Celsius for simplicity, right? So now I have the temperature, I have the pressure. So now I need to go into table A6 at P1 and T1. Go into table A6. So on to A6. Remember that we have these subtables for superheat. So here is the 3.5 megapascal subtable. We read down to the 250 line, which is the third line down. And it's this data right here where the cursor is. So we need two things, right? We need specific volume and we need specific internal energy. So let's just write them both down. V1 is 0.05875 cubic meters per kilogram, and U1 is 2623.9 kilojoules per kilogram. So there's my data at state point 1. Again, I want to remind you that if I've made a math error somewhere or pulled some data incorrectly out of the tables, I would like somebody to let me know that so that I can fix it. After all, it's all getting recorded. So, yes?
The blank line on the table, so if we needed like a 225 degrees, for example, how would we do that?
That is an interesting question. First of all, you wouldn't, because it turns out that well, I mean, maybe I should take that back. What you could do is you could interpolate between the saturated vapor conditions and your superheat conditions. So you would have to go in here at saturation, which now corresponds to 242, right? So these are your saturation conditions. These are your conditions at 250. So you're interpolating between, let's say, 242 and 250. Now, that's why I said 225 wouldn't happen, because 225 already puts you into the two-phase region. But let's say the temperature was 245. Right? So 250 obviously isn't right. The data at 242.56 is not right either. You're in between the two. So you would just do the interpolation between those two entries. Okay. All right, so next. We have our data at point 1. Let's just find all of our thermodynamic property data. It's going to be easiest that way. So at point 2, we have a saturated liquid at 3.5 megapascals, right? It's a constant pressure problem because it only hits the stops when we finally get to saturated liquid. So at P2, which equals P1, and saturated liquid. All right, so this is the pressure data, so we have to use table A5. We don't need the internal energy at point 2, so actually we do, don't we? Because they have asked me to find the heat transfer from 1 to 2, so I guess I better write it down. All right, so we need V2, which equals VF, and that is 0.001235. And U2 is UF, which is 1045.4 kilojoules per kilogram. All right, so that's all the data we need to state point 2. Let's do the same at point 3. So at V3, which equals V2, correct? And at T3, and T3 was 200 degrees Celsius. Well, now we're given temperature data, so that means we're going to have to go to table A4. I don't really need to do the test because I simply know, based on the problem statement, we're a saturated liquid, and then we're cooling. You know, you have to move downwards, and that's going to put you definitely into the two-phase region. I could do the test if I wanted to, just to prove that, but not really necessary. You may want to do it just to make sure. Nonetheless, what we would find is that at 200 degrees Celsius, my specific volume is greater than VF and less than VG. Okay, I mean, we can see that if we go back up to the table. I'm going to have to go up to the table anyway to get my numbers, but all right, so here's A4. My temperature is, whoops, I need the other page. Yeah, here we go. So, you know, VF is 0.0011, and my specific volume at point 2, which equals my specific volume at point 3, is 0.01235. So 0.012 is greater than 0.011, so clearly I'm above VF, and it's a two-phase mixture. So it's a two-phase mixture. How do we find the data we need? Well, first keep in mind that we really only need, well, actually we need two things, don't we? Really three things. They've asked me for the pressure, they've asked me for the quality, but then they also want to know what the internal energy is. Actually, I want to know what the internal energy is so that I can solve my first law. So three things I need. The first one's easy. It's two-phase, so P3 is just Psat at 200 degrees Celsius, so that gives me 1,554.9 kilopascals. Okay. To find the quality, I'm going to have to use the specific volume data for the two-phase mixture. V3 is VF plus the quality at 3 times VFG. So this is how we find the quality. V3 is V2, it's known to me. So this is just 0.001235. At 200 degrees Celsius, VF can be looked up, and VF is 0.001157. The quality is what we're trying to find. VFG is just the difference between VG and VF. So VG is 0.12721. So that's VG. And VF is the same number we have, 0.001157. Anyway, go through some math. We find that the quality at point 3 is 0.00062. So it's extremely low quality, but still it's a two-phase mixture. So now we have the quality. And now let's find the internal energy. So U3 is UF plus the quality times UFG. So again, just look up the numbers. Everything should be in the table over there. UF is 850.46. Actually, we had that from before, didn't we? Oh, no, we didn't. We're at a lower temperature, so we didn't have that from before. The quality is 0.00062. UFG is 1743.7. And if we just go through our math here, we get 851.55 kilojoules per kilogram. All right, so not much left to do but to go through our various equations. Next, let's find the work. So the work for this particular problem is, let's see, we wrote it down before. It's just our boundary work from 1 to 2. I mean, technically, it's the work from 1 to 2 plus the work 2 to 3, but there is no work from 2 to 3 because it's constant volume, right? So maybe I'll just write that. Boundary work is work 1, 2 plus work 2, 3, but that's equal to 0. So that's work 1, 2, which is mass times pressure times V2 minus V1. So let's just plug in the numbers that we have here. Mass is 0.35 kilograms. Pressure, I'm going to put the pressure into kilopascals instead of megapascals so that all my conversion factors are just identities, just ones. In other words, I don't have to worry about conversions. And then the specific volume change. So we have 0.001235, and then minus 0.05875. And those are meters cubed per kilogram. Again, the units here are the same units we had in the previous problem. Kilopascals basically converts into kilojoules per cubic meters, what it converts into. And we end up with minus 70.45 kilojoules. Now, before we move on, does the minus sign make sense? Well, it should, right? I mean, negative work means work is being done to the system. In other words, the piston is pushing into the system. Work is clearly being done to the system. The volume is shrinking. So yes, the negative sign is proper. And next, we want to find our two heat transfer terms. So again, these equations are already in your notes. So we have change in internal energy plus the work from 1, 2. So again, it's just a matter of plugging in the numbers. 0.35 times, what are our numbers? I've lost my numbers. Okay, here we go. Yeah, thanks. 145.4. And U1 was 2623.9. I forgot my units. I don't want to forget my units. And then the work is minus 70.45. So if we go through our mathematics, we end up with minus 622.9 kilojoules. Hello. And then lastly, we find the heat transfer from 2 to 3. And the heat transfer from 2 to 3, well, again, this is just mass times change in internal energy. Oh, I'm sorry, I'm not doing 2 to 3, I'm doing 1 to 3, right? I'm trying to find the total heat transfer. I could find Q23 if I wanted to, but that's not asked of me, so I'm not going to waste the time. So Q13 is mass times U3 minus U1, and then plus the work from 1 to 3 which equals the work from 1 to 2, which still equals the boundary work. So it's everything we had before. So 0.35 kilograms. Yes. And then U3 is 851.55. U1 is 2623.9. And then plus the 70.45 again. And this gives me minus 690.8 kilojoules. So there's a nice long fun problem. Yes?
You could also find the total heat from 1 to 3 who did Q12 plus change in U3 minus U2.
I'm not gonna say for sure. I would have to go back and look at the equations and see. But we went through a derivation of these equations, and it would seem that there are certainly ways to simplify if we needed to, or to just give us a different version. I'm not going to answer that. I would have to write the equation down and see if it works out properly. But yes, there are certainly ways you can get your answers that are a little bit different than the way I've done here. For instance, sometimes the students who are trying to find the work, they calculate the heat transfer based on the enthalpy for a constant pressure process, and then they calculate the heat transfer using the internal energy plus the work, and they equate them, and then they get the work that way. So they never actually have to calculate the boundary work. They just solve for heat 2 different ways, and the boundary work is one of the unknowns. So yeah, there's different ways to solve some of these problems. Questions? All right. Well, one other thing then that I want to do today, and this is just to be consistent with your syllabus. By the way, we're done now through section 4-2, and we're not going to talk anymore about this material. Everything that we covered up until right now is fair game on the midterm exam, and again, the midterm is a week from Monday, so you got plenty of time to study for it. Again, it's a closed book, closed notes exam, except you'll have property tables that I'll hand out to you. Anyway, so starting now, we move on to the next section of chapter 4, and this deals with something that's called specific heats. So we're not completely leaving behind these closed system problems, but we have to ask ourselves, what if I have something other than water or the refrigerant, 134A? For instance, what if I have, how about a gas, like an ideal gas? How do I solve first law problems for ideal gases? They're just as applicable to those types of problems as they are to any other type of problem. Well, the answer is specific heats. It's not going to be clear yet what specific heats are or why we use them, but I will tell you that we are going to have to solve first law problems. Some of these first law problems are going to be involving ideal gases, and because there's so many gases, there isn't nearly as much property data available for this wide variety of gases as we have for, say, the refrigerants or for water. So oftentimes you just don't have property tables like these, like the ones we've been looking at here on the board. We're going to have to use another method, and that involves what's called specific heats. Okay, so specific heat. Now, specific heats are properties. And there's actually 2 of them. Okay, one is called specific heat at constant pressure, and one is called specific heat at constant volume. The one we call specific heat at constant pressure, we're going to use Cp, and the other one that we call specific heat at constant volume, we're going to call Cv. Now, specific heats are properties, but these are different than most of the other properties we've seen. remember when we talked about enthalpy, and I defined enthalpy as U plus PV, and I simply said that since U and P and V are all properties, then any mathematical combination of those properties is also going to be a thermodynamic property. That's really what specific heats are. They're different combinations of other properties. We define the specific heat at constant pressure as the partial derivative of the specific enthalpy with respect to temperature holding pressure constant. And we define the specific heat at constant volume as a partial derivative of the specific internal energy with respect to temperature holding volume constant. The reason we call these specific heats at constant volume or at constant pressure is not because it has anything to do with constant volume or constant pressure processes. That's not at all important. They're called constant pressure and constant volume because of the way that we take the partial derivatives. Right? When you write a partial derivative like this, that means we're taking the derivative of one variable with respect to another, holding this third variable constant, right? Specific heat at constant volume, we're taking the partial of U with respect to T, but we're holding the volume constant. So that's why we call these specific heat at constant volume or constant pressure. So please make sure you recognize that we're not talking about constant pressure or volume processes. We're talking about new thermodynamic properties that are combinations of other properties, and we're going to have to figure out how to use them to solve some realistic problems. Now, this will have to wait until next week, so we'll talk about it later. Anyway, at least you've been introduced to this, and we'll deal with it in more detail. So I've got homework up here from last time. Please don't forget to pick up your work. If anybody has problems with anything, please come see me in my office hours. So far, I mostly just have to sit there by myself in the office hours because nobody has questions. So that's great. I guess you know the material really well. But if anybody has questions, please come see me. Your exam's in just over a week. And while it's just one midterm, it's still worth a quarter of your grade. So it's significant. So if you have questions or problems with anything,